From the four forces that emerged from the Big Bang, the weirdest of them all is the weak nuclear force. Weak nuclear force is the force of the shortest range of all the forces, and we will explain why soon. It's also the weakest force. The weak force is mediated by W and Z bosons, and these are force carriers just like photons for electromagnetic force and gravitons for gravity and gluons for the strong force. The weak nuclear force and the electromagnetic force were conjoined into one force in the early moments of the Big Bang, and so they have quite a number of things in common. Let's then compare. The photon that mediates the electromagnetic force is massless, but the W and Z bosons that mediates the weak force is massive. In fact, they are much heavier than the protons and neutrons. Photons have no charge, but W bosons could exist as positively or negatively charged, while the Z boson is neutral. Using Feynman diagrams, we could establish how the weak nuclear force operates, and we would realize it is quite similar to that of the electromagnetic force. Weak nuclear force is the force responsible for nuclear fission, fusion, and nuclear decay. Decay occurs when the nucleus undergoes transformation, emitting particles. Now, nuclear decay is the process whereby unstable atomic nuclei loses energy to become stable. So, they are unstable because of their proton-neutron ratio. Now, this is a very important aspect of nuclear decay. If the proton-neutron ratio is not close to 1, that is, if the number of protons and number of neutrons are not equally the same or are not closely the same, then the whole atom is unstable. Heavier particles could decay into lighter particles because they are unstable and have excess energy, therefore energy enough to produce the W plus, W minus, and Z bosons. As explained in some previous video, particles would like to be in their ground state naturally. And so, when they become unstable in a state they are not supposed to be in, there would be a weak force around to say hello through the emission of these force carriers by the quarks. Beta decay occurs when a nucleus emits an electron. Scientists noted that the energy of the emitted electron was not always the same. The energy difference of different beta decay processes was a continuous range, and so quite later, after the nuclear decay concept was established, Enrico Fermi, that guy again, explained that the energy difference was due to a particle produced after the electron was emitted. And that particle was a neutrino. The neutrinos carried away some of the energy, and this energy was dependent on the propagation of the neutrino and the electron after the decay of the W boson. W and Z bosons interact with quarks. An example is when a W boson is produced, it could interact with a down quark to produce an up quark, and therefore emitting an electron and a neutrino. The weak nuclear force is short-ranged because the force acts only in quarks. Within quarks. While even the strong nuclear force acts between protons and neutrons. The weak force is responsible for fission because there is a constant transformation of protons to neutrons as the nucleus is being fired with neutrons. Same way, its transformation ability helps to initiate the nuclear fusion process. Weak nuclear force is weak because even at the speed of light, these force carriers could travel only a fraction of a width of a proton. And since they are so massive, light travel is impossible. And so they are all almost non existent. Weak nuclear force is the force that was used to prove that spin was actually a fundamental property of particles due to the identification of the movement of neutrinos produced during the decay process. Yes. This is what we have for you for one of the weirdest forces or topics in particle physics. Thank you all so much for listening. Once again, this is Einstein in a flash.